Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Phonons and Electrical Transport in Semiconductor Nanoparticles from the paper Physics at Nanoscale. So students, the learning objectives of this module are: first, the dependence of elastic constants on the lattice constants is discussed. Secondly, the theory of acoustic phonons in nanoparticles will be discussed. Next, the phonons in indium arsenide nanoparticle in gallium arsenide matrix will be discussed. The Exciton-acoustic phonon coupling in nanoparticles will be discussed. Next, the nanoparticles between the two metallic contacts will be discussed in this module. Lastly, we will also discuss a nanoparticle with a single contact. So let us start with a basic introduction about the module. Dependence of elastic constants on the lattice constants. So the highly efficient optical transmission with high quantum efficiency identify several applications for semiconductor based nanoparticle. However, the loss of coherence due to the dephasing is an extremely important issue. So the interaction of excitons with lattice vibrations, in particular the acoustic phonons, is responsible for dephasing. The exciton-acoustic phonon coupling is described by deformation potential coupling. So in a semiconductor nanoparticle, the confinement of carriers or excitons is generally achieved by embedding a small band gap in a larger band gap material. Say for an example, indium arsenide in gallium arsenide. As the band gap decreases, that is, it is decreasing with increase in the lattice constant, to achieve confinement of exciton material with larger lattice constant has to be embedded and forms the region where the exciton will be confined, implying that nanoparticle is compressed. The acoustic phonons, they are described by elastic constants. This figure shows how the values of elastic constants of zinc blende semiconductors varies with the equilibrium lattice constant and decreases with the increasing volume of the unit cell. So, however, due to intrinsic strain in compressed nanoparticles, the elastic constants are modified. So, the compression of the nanoparticle material results in an increase of the elastic constants, that is, the material become harder. Theory of acoustic phonons in nanoparticles. In continuum elasticity model to describe the acoustic phonons, the small volume elements and their displacement UR under deformations are considered. So the components of the strain tensor epsilon are given with respect to the displacement for a homogeneously deformed system by epsilon KL equal to half multiplied by del UK by del XL plus del UL by del XK plus 2 multiplied by del UK by del XL multiplied by del UL by del XK. So the relation between the stress epsilon and strain sigma is given by sigma ij equal to summation over KL over del rho naught multiplied by phi by del epsilon KL multiplied by delta ik minus del ui by del xk multiplied by delta jl minus del uj by del xl, where rho naught is the equilibrium mass density and phi is the free energy density which can be expanded around the equilibrium in terms of the strain tensor. So rho naught phi equal to half multiplied by summation over ij equal to 1 to 6 Cij multiplied by epsilon I multiplied by epsilon j plus 1 by 3 factorial multiplied by summation over ijk equal to 1 to 6 Cijk multiplied by epsilon I multiplied by epsilon j multiplied by epsilon k plus so on. So the expansion coefficients Cij and Cijk are the second order and third order elastic constants respectively. So the effective number of independent elastic constants is reduced to symmetry. In the case of zinc blende semiconductors, there are only 3 independent second order elastic constants, that is C11, C12 and C44. Now the equation of motion for the displacement is given by minus omega square rho r multiplied by UIR equal to summation over J over del sigma I R divided by del X J. So the stress-strain relation using the free energy density expansion reduces to epsilon ij equal to half multiplied by del ui by del xj plus del uj by del xi, and according to Hooke's law, sigma I equal to summation over j Cij multiplied by epsilon j. So if we consider only with the isotropic medium, only 2 elastic constants are independent. So C12 equal to C11 minus 2C44. Then the wave equation in this isotropic pedia becomes minus omega square rho r multiplied by ur equal to minus 4 dC44 as a function of r multiplied by ur divided by dr multiplied by ur by dr plus d by dr of C11r multiplied by dur by dr plus 2ur by r bracket close. When the semiconductor nanoparticle is embedded inside the another semiconductors, pseudomorphically. Then the lattice matching at the interface leads to intrinsic spin due to difference in lattice parameters between the nanoparticles and the host matrix. So a typical lattice mismatch is of substantially higher orders in the free energy expansion contribute significantly. So under this approximation, by preserving the crystal symmetry, that is hydrostatic strain, the effective strain dependent elastic constants are calculated. So they are used as the input for equation discussed previously, where their spatial dependence is due to the change of the material and the spatially dependent strain, that is Cij equal to Cij multiplied by epsilon r. So the calculation of elastic properties of small periodic cells is possible directly by employing ab initio density functional theory. So here the focus is on the calculation of effective elastic constants for hydrostatically deformed indium arsenide and gallium arsenide unit cells by density functional perturbation theory. So the result of the calculation is shown in this figure, where the dependence of the effective elastic constants on the local lattice constant is given for indium arsenide. So this figure shows the dependence of the elastic constants on the local lattice constants given for indium arsenide and gallium arsenide. So the elastic constant C11 and C12 decreases as lattice constant increases. So the C44 shows strong bowing is due to the non-linear dependencies. Phonons in indium arsenide nanoparticle embedded in gallium arsenide matrix. So this figure shows the energy dependence of the phonon amplitudes for two spherical indium arsenide nanoparticle with a radius of capital R equal to 5 nanometer and capital R equal to 10 nanometer in an infinitely extended host lattice. The values for the different parameters used to calculate the results are presented in this figure and are also tabulated in this table, where the values of ME, MHH average, DC, DV, rho and A0 are being given for gallium arsenide, indium arsenide and S-indium arsenide. So the scaling of all coordinates xj equal to 1 minus alpha multiplied by xj for indium arsenide, gallium arsenide matrix is used to characterize the hydrostatic deformation alpha, which can be determined from the static solution omega equal to 0 of the equation minus omega square multiplied by rho r multiplied by ur equal to minus 4 derivative of C44R by dr multiplied by ur by r plus d by dr of C11R multiplied by dur by dr plus 2ur by r, where the lattice mismatch A0 can be given by alpha naught is equal to alpha naught multiplied by C44, or we can say that is alpha related to alpha naught by alpha equal to alpha naught C44 gallium arsenide divided by C44 indium arsenide minus C44 gallium arsenide plus 3 by 4 C11 indium arsenide, where the lattice mismatch alpha naught can be given by alpha naught equal to A naught indium arsenide minus alpha naught gallium arsenide divided by alpha naught indium arsenide equal to 6.8%. Alpha naught indium arsenide and alpha naught gallium arsenide are the equilibrium lattice constants of indium arsenide and gallium arsenide respectively. So the relaxed lattice constant alpha of the embedded indium arsenide nanoparticle, which is compressed hydrostatically due to lattice mismatch, is therefore given by alpha indium arsenide equal to 1 minus alpha multiplied by alpha naught indium arsenide. Under this approximation, the volume of the host material gallium arsenide remains unchanged with a compensating radial compression and a lateral dilation. In the case of gallium arsenide matrix, solution UBr of the above equation with no spatial dependence of either elastic constants or mass density can be given by UBr equal to JL multiplied by KBr, where JLx, that is this function, is the spherical Bessel function and the wave number KB is related to phonon energy, that is E equal to h cut nu LB multiplied by KB, where nu LB is the longitudinal sound velocity in gallium arsenide matrix. In the case of indium arsenide nanoparticles, the spatial dependence leads to a modification of the phonon modes. So the displacement UR around the origin inside the nanoparticle is scaled by an energy dependent prefactor. That is, UR equal to A prime as a function of E multiplied by Ji as a function of KdR. So AE will be equal to A prime E multiplied by nu B by nu D, where we can express these as nu 1B and nu 1D. These are the longitudinal sound velocity in indium arsenide nanoparticle and gallium arsenide matrix respectively. So this prefactor is the main source of the changes in the electron-phonon coupling in a nanoparticle. So hence AE prime equal to 1 in gallium arsenide matrix. Exciton-acoustic phonon coupling in a nanoparticle. In the case of semiconductor nanoparticle embedded in a matrix, the coupling through deformation potential is only important for electron-hole acoustic phonon or exciton-acoustic phonon coupling, which is represented by exciton-phonon coupling function Fe equal to summation over nu delta as a function of E minus h cut omega nu multiplied by m nu 11 the modulus the whole square, where m11 is the exciton-phonon matrix element for the lowest electron and hole sublevels phi EL as a function of Re and phi HL as a function of RH, which couples only when L equal to 0 acoustic nodes nu. So psi L as a function of Re RH equal to phi E1 as a function of Re multiplied by phi H1 as a function of RH. So m nu 1 component will be equal to the double integral psi 1 star Re RH multiplied by dc Re divergence of u nu Re minus d nu RH multiplied by divergence of u nu RH. This is multiplied by psi 1 Re RH multiplied by dRe dRH, where dc and d nu are deformation potential constant for conduction band and valence band respectively. Now putting the equation of that is given by the equation for UBR in the previous equation, we get Fe equal to E cube by 4 pi square h cut cube rho b nu lb to the power 5 multiplied by the modulus of integral 0 to infinity dr r square multiplied by dcb phi e1 r the square minus dvb phi h1 r the square multiplied by j naught kbr the whole square. Electron-phonon coupling for two different sized nanoparticles. So this figure shows the exciton-phonon coupling function for two different sized nanoparticles. As expected, decreasing the size of the nanoparticle from r equal to 10 nanometer to 5 nanometer leads to a stronger coupling. So students, let us now discuss the electrical transport through a nanoparticle, that is nanoparticle between two metallic contacts. As we have discussed before, nanoparticle is a 0D conductor, semiconductor and electrons are confined in three-dimensional square or spherical potential well. The energy levels are discrete and depends on the nanoparticle semiconductors in addition to confinement potentials. So this figure shows a typical square well in a semiconductor based nanoparticle with its energy levels. Each energy level corresponds to a different molecular orbital and all the energy levels are measured with respect to the vacuum energy, typically defined as the potential energy of a free electron in a vacuum. So as discussed before, the eigenstates for electrons and holes can be considered as molecular orbitals. Hence, the lowest energy level can be called as the highest occupied molecular orbital HOMO, and highest energy level of holes can be called as lowest unoccupied molecular orbital LUMO. So the below figure shows a square well approximation of a nanoparticle. Electron and hole energy levels are shown relative to vacuum energy, and the band gap or HOMO-LUMO gate, that is ET equal to IP minus I multiplied by E minus E multiplied by A. So according to the bottom-up approach, the below figure defines the ionization potential IP of a nanoparticle as the binding energy of an electron in the HOMO, electron affinity EA as the binding energy of electrons in the LUMO. So ET is the HOMO-LUMO gap, whereas EG is the band gap of the semiconductor. Now, the contact in this problem is treated as a reservoir with large number of electrons compared to the nanoparticle, and all the electrons in contact, they are in equilibrium. So the metallic contacts are characterized with the work function phi f, which is the energy required to promote an electron from the Fermi level in the metal contact to the vacuum energy as shown in this figure. So when an electron is added to contact from a nanoparticle, or when an electron is removed from the contact, ideally contact will be in non-equilibrium. But due to large number of electrons, the deviations from equilibrium are small, and it can be approximated that the potential in the contact is uniform. For example, consider a large metal contact. Its resistance is very small, and consequently any voltage drop in the contact must be relatively small. So in the absence of applied bias, the isolated contact and nanoparticle, they are at the same potential, and when the contact is connected with the nanoparticle, the combined system must be in equilibrium, having the same Fermi energy in both the contact and the nanoparticle. Since the Fermi levels changes with the addition or removal of an electron, equilibrium is restored by charge transfer between the metal contact and the molecule. As the charges are transferred, the potential of the contact relative to the molecule changes, resulting in the shift in the relative vacuum energies. This is known as charging, which also changes the Fermi levels as electrons fill some states and empty out some states. Both the charge transfer induced effects, charging and state filling, can be modeled by capacitors. So students, let us summarize what we have learned in this module. First, the dependence of elastic constants on the lattice constants has been discussed. Second, the theory of acoustic phonons in nanoparticles has been discussed. Thirdly, the examples of phonons in indium arsenide nanoparticles in gallium arsenide matrix is being shown. Next, we have also studied the exciton-acoustic phonon coupling in a nanoparticle. Lastly, students, we also discussed the nanoparticle between two metallic contacts and with a single contact has been studied. Thank you.